all in the post-lunch session. And the first speaker in the post-lunch session is Dr. Namrata Shukla. And it's my pleasure to introduce her. She did her BS and MS from University of Gorakhpur, and then she moved to University of Allahabad for her PhD. And after completing her PhD, she did a couple of postdocs in Europe and the North America. And she recently joined the Kashi Hindu Vishwavidyalaya as assistant professor in the physics department. And her expertise is basically quantum optics. So with this small brief introduction, I invite Dr. Shukla for the presentation. Dr. Shukla.
Thank you, Ashwini, for introducing me so nicely. And so first and foremost, I would like to thank Professor Panigrahi and the team, which includes a lot of people from ICER Kolkata, I'm sure, for having such a great platform where almost all the experts in the field are, available at some point of time, and they were able to interact with the students, a pretty good number of students. So I have been following different talks. So thank you so much for giving me an opportunity to speak at this platform. And so I will start sharing my screen and then get to it. I would just like a confirmation if you can see my screen already.
Yes, we can see your screen. Yeah.
Good, thank you so much. I'll go in the full screen mode. Is there a way to minimize this? Okay, so as Ashwini already told, I do work at the Banaras Hindu University as an assistant professor. In fact, it's not been too long when I joined here. And I was told to talk about a little bit about Berry phase because probably the session that my talk was scheduled in, or probably the day, is dedicated to Berry phase. So I will be talking a little bit about Berry phase in the beginning, a couple of slides, and then I will move on to my actual topic of the talk, which is sum uncertainty relations and quantum entanglement, of course. And in this as well, I will be mostly focusing on the sum uncertainty relations and for a particular class of sum uncertainty relations that we have derived in one of our work. And less about entanglement, but definitely I will talk about entanglement as well. So I'm assuming that there are most of the people here are students. So even though this is not a typical school talk, and I apologize for that, I have tried to construct it in such a way that if you have done your group theory course and basic quantum mechanics course, then you should be able to follow a lot of it already. So that is the idea. And with this, I will get started. So yeah, this is where I do work. I think most of you might be already familiar because it is a popular university. This is the physics department. And once the pandemic is over, of course, you're most welcome to visit. Okay, so after this, I'll move on to the talk. Please don't worry about all these bullet points because I know the phrase bullet points kill, actually. So don't worry about this. I have tried to structure the talk in rather a simple manner and not cover a lot of technical details, so it is easier for you to follow. So firstly, I will talk about Berry phase, as I said, and then I will move on to the actual topic of uncertainty relations. So, and in the uncertainty relation and entanglement part, I'll give some background, and then I will tell you why do we need what we are trying to, produce in this work. And of course, to understand that, we need some basic ideas. So that will be covered in some slides, which will be mostly group theoretic and representation based concepts. And then I will state the exact mathematical problem. What do we try to achieve and what did we actually achieve? Because that is not exactly the same. We could do it for a subclass of what we were aiming to be the problem. And then I'll talk about the methods, how we do it, which is, again, a little complicated if you get to the higher dimensions, but If you think about simple, lower dimensions, then it will look easy. And then I'll talk about the results, discussion, and the conclusion. Okay, so with this, with my tribute to, to the Berry phase, or let's say my dedication to the Berry phase, I will talk a little bit about it. What is Berry phase, basically? It is also called geometric phase, Pancharatnam phase, or Pancharatnam Berry phase. And the simplest way to understand the idea is with these two pictures. So I have talked about parallel transport here, and I mean parallel transport of vectors. So when I'm saying parallel transport, let's look at a plane. So in a plane, let's say that there is this curve here, which is basically a circle. What I'm trying to do is I'm trying to start, let's say, from this point. Is my mouse visible, by the way?
Yeah, it's visible. Yeah, yeah.
So I'm trying to start at this point and slowly go over this circle and come back to this point. Okay. And when I say slowly go over this circle, I'm trying to, let's say that I have a vector in this direction and I'm slowly going over this whole cyclic path. I'm keeping this vector parallel to the original vector at each point, right? And I do move on this circular path and get back to the point where I started. So when I do this on a plane, I will end up having the same vector which I started with. But if I do the same thing on a curved surface, for example, here on a sphere, let's see what happens. So we started, let's say, for example, at this point, the red vectors are, the red arrows are the vectors that I'm trying to transport, trying to move across a particular curve or cycle, so to say. So I started here and I kept doing the parallel transport of vector. And when I say in this case, the parallel transport, I'm trying to keep the vector parallel to the last point locally. Okay, so when I say this is what is meant by a slow enough process so that you can keep it parallel. So the vector again gets transported parallelly over this whole cycle, okay, from here and goes back to this point. So when I end up at this point, it seems I did not get to the same vector where I started. It makes an angle with the original vector, right? So what happens basically that if I did a parallel transport like this on a parallel transport of vector on a curved surface, I end up with a phase, okay? And that phase, to understand it most simply, is Berry phase or geometric phase. So apparently this phase depends on what is the cycle that I'm choosing, okay? So it must have to do with the geometry. It must have to do with the path that I'm choosing, and that is why it is also called geometric phase. And this is again the simplest picture of it to look at it. Now, it is also called Pancharatnam phase because it was not per se very firstly noticed in its most raw form by Berry, but it was rather done by another scientist called Tako and Pancharatnam. So I will talk about the Pancharatnam works. I mean, I'll just give a couple of lines about it, basically how he did it. But this is Berry phase, and it is also called geometric phase. It is also called combinedly Pancharatnam Berry phase, or also Pancharatnam phase, to be honest. Okay, so with this basic idea, I will jump to this particular paper, which was published in the Proceedings of the Royal Society of London. Here is the reference. And this talks about, so to say, a quantal phase factor. So it gives a picture for the quantum mechanical systems, how this kind of Berry phase is important. So this is a very important paper. But here, down, if you can see, the second one, it's not visible completely. But this paper here is Pancharatnam's paper, in which he was basically trying to look at the interference in polarized beams. And what he observed is that in case of interference, I mean, he did he did some work, and then he found out that the expected phase difference that he was expecting basically was not the same. It had an additional phase when he was looking at the interference in case of polarization, and he was using Stokes parameters to describe the polarization basically. So that is how that was the raw version of this phase when it came into the picture first. But then, of course, Berry had put it on very firm footing, and it was well defined for quantum mechanical systems, and it is very relevant. So how does it work if you want to think about, let's say, quantum mechanical systems? Even before that, maybe I'll define it in one line. So if a system undergoes adiabatic change, when I say adiabatic change, I mean slow enough change, over a cycle, it acquires an extra phase, which is what I demonstrated, which is what I explained here. So that phase is basically the phase that we are talking about. Now think about a quantum mechanical system. Let's say that the quantum mechanical system exists and it has an environment. There is a Hamiltonian that is describing the system and the environment together. Now we start to change the environment very slowly, okay, which means the adiabatic change. And this is very slow perturbation that we put the system under, or change the environment very, very slowly. And what happens is H changes with that. Okay, but given the perturbation is very slow, if we want to get the state of the system at any particular point, then if we have the instantaneous Hamiltonian, the system will be in the eigenstate of that. Okay. Now we try to get back to the original Hamiltonian where we started. And if we get back to the original Hamiltonian following this slow process, we will end up with a phase. And this will be in addition to the dynamical phase. Let's say that if we think about the quantum evolution, the general e to the power I h t, in addition to that dynamical phase, there will be another phase. And that is our geometric phase. It depends on the geometry of the system. Okay, so this is the idea of the Berry phase. Now it has wide applications in physics. Traditionally, it was attributed to the foundations of quantum mechanics in the Berry's paper, for example. But these days, it is apparent and it is being used in a lot of fields of physics, such as optics and condensed matter physics. It is widely used. Then in high energy and particle physics, it is used, fluid mechanics, gravity, and cosmology. And of course, most importantly, that we are concerned with is quantum information and quantum computation. So we will not talk a lot about it, but maybe I'll choose a couple of words to tell you that how it is used in quantum information and quantum computation. So here is a paper by Cohen in Nature Review that basically talks about applications of geometric phase or Berry phase in different areas of physics, and that's a very good review. I would recommend the students to go through that if you are interested in this. And in quantum information and computation, basically there are two things that I would like to cover. One, the connection of geometric phase with entanglement. So I'm very sure you have heard about quantum entanglement at this point, because there were a lot of talks on quantum information and how things work in quantum information and quantum computation. So geometric phase has a connection with entanglement, and it has been established by different people in different ways for different type of systems and so on. So for example, this first paper here, which is by Sjoquist again in PRA in 2000, this talks about the connection of geometric phase with entanglement for the spin half particles. Okay, I'm actually wondering a little bit why I can't see this whole thing in here. I should be able to see. Okay, so in this case, basically, a pair of spin half particles are prepared in an entangled state in this particular paper that I'm talking about. And they are put under adiabatic change with an external time independent magnetic field, so slow perturbation. And what is observed is the geometric phase of the entangled system basically reduces to the geometric phase of the one system in the product state. So, of course, you can study the states and what is happening to the geometric phase if the systems were separable and then it is entangled, so the evolution altogether. And this reduction of geometric phase was basically explained in this particular paper by, some total reduction in the degree of polarization of that particular particle that is getting affected and so on. So, of course, if you are interested in the details, you can go to the paper and see. But this is not the only paper. I chose this, but there has been different studies for spin half particles, especially to connect it with the geometric phase. Now, the other thing is its applications in quantum computation. So this paper here is an article in physics. And if you start reading this article, you can get many more articles that talk in more detail about this thing. So you know that maintaining coherence is one of the biggest challenges in quantum computing. Apparently, in this work, what they say is this coherence can be maintained better if you used geometric phase to basically, mimic the quantum gates. So the effect of geometric phase, and that basically does moving a set of quantum parameters around a curved parameter space, because that is what happens in geometric phase. So you construct or use a quantum gates by applying that particular effect, and you can do better in quantum computing. So this is just a glimpse. Of course, I have not presented it in detail, but there are a couple of these things that I decided to choose. So if you are interested, you can go to these papers and then you can get into the cross references and find out that there are a lot of papers that connect entanglement with geometric phase, and also it appears very well in improvement of building of quantum computers, let's say, so in quantum computing. Okay, so with this, I will stop at this topic, and now I will move on to my actual topic, which is uncertainty relations and entanglement. So what do we know about, let's focus on uncertainty principles first, or uncertainty relations thereby. So what do we know about uncertainty principle? We all know, we have done the textbook study of uncertainty principle, that it was given by Heisenberg, and it is a statement that tells precisely about the fundamental limits to the measurement of complementary observables. So if there is a set of incompatible observables and you want to make simultaneous measurements on them, there will be a limit that dictates the precision of that those measurements, right? So that is your uncertainty principle. Now, this was given by Heisenberg, of course. And then uncertainty relation, as we learn in our textbooks, is a mathematical formulation of the same idea. Now, it is not as simple as we think, because lately in the last 2 decades, there has been a lot of debates about what Heisenberg thought of the uncertainty principle and how he mathematically gave the formulation of this, which we do in the textbook, of course. But I'm not going to get into those debates. 1 or 2 of my works is related to that, but I will not talk about that today. So anyway, Heisenberg had given his version of uncertainty, mathematical formulation of his version of uncertainty relation, which originates from uncertainty principle, basically, and we know this. And then after that, it was put on firm footing by Kennard, another scientist named Kennard, and then it was rigorously proved for any 2 general observables A and B. So not just for position momentum or time energy or anything like that, but any 2 general observables that were incompatible. And it was proved by Robertson, and this is how it reads. Of course, then after this, there was an additional term on the right-hand side that was given by Schrodinger-Robertson, and that version is called Schrodinger-Robertson version of uncertainty relation. But here we are concerned only with this. So as you can see that when we write down this uncertainty relation, there are these terms which talk about the fluctuations in the observable A and B, and they're defined like this. These are state-dependent terms. Also, the right-hand side has a commutator of A and B and is a state-dependent term again. Okay, so okay, fine. This is okay. We have state-dependent terms in this uncertainty relation, but we can write it down for any two arbitrary observables, A and B. Now, what is the problem with this? This is generally a product uncertainty relation, just like delta x delta p is greater than or equal to h cross over 2, and so on, right? So this is a product uncertainty relation. Now, I am going to be talking about sum uncertainty relations, and why is a sum uncertainty relation needed if we have the product uncertainty relation? What is the problem with the product uncertainty relation? So some people spotted in last couple of decades that this product uncertainty relation can get trivial for certain states. Of course, it is state dependent. It can get trivial, for example, if the state psi that we are choosing is an eigenstate of any of these two observables, right? So if your psi is an eigenstate of A or B, then both the sides are going to get to 0. You can do this simple calculation and you can see that it will get trivial. So what do you conclude of the uncertainty relations in that case? Now, that triviality or the right-hand side getting to 0 was one reason why the birth of entropic uncertainty relations took place. And they are again sum uncertainty relations. I'm not going to get into the details because that is a whole different field, entropic uncertainty relations, but they deal with different types of entropies. And they're very popular again in quantum mechanics, so Shannon entropy, Rayleigh entropy, and so on and so forth. But any entropic uncertainty relation that you see is going to be sum uncertainty relation. Now, okay, so we are also going to be talking about such sum uncertainty relations. But let's get back to the problem that we were talking about earlier. If we're talking about two incompatible general observables A and B, and I told you what the problem of triviality is, then what the solution is. Apparently, the solution was given by Makone and Pati in this PRL paper here in 2014, not too long ago. And this was one of the motivations why I did this work that I will be basically presenting to you. So what they did in this is they gave some uncertainty relation. You see, this is an inequality, and you see on the left-hand side again we have the fluctuation terms, okay, for any two incompatible observables. But we talk about the sum, and then we put a bound. Again, this is state dependent. The terms are state dependent still, but they remedied this problem in one sense that when they wrote this, they introduced the state psi perpendicular or psi orthogonal, which is basically a state orthogonal to state psi. And if you have this, if you can find such a state, then in that case, the triviality problem will be solved. But the triviality problem will still exist for two cases, and you have to avoid these two cases. One of those cases is the psi perpendicular should not be orthogonal to this whole thing. So A plus minus IB psi, because then that will make it 0, right? And the other thing is the state psi should not be common eigenstate of both the observables A and B. So if you can avoid these two things, then this solves the problem. You have to choose the psi perpendicular smartly. Okay, so this was, why I talked about this work is this was one of the works to remedy the problem of triviality. Okay, now to talk about entanglement a little bit. So again, I will not introduce what is entanglement because I'm assuming you know this by at this point. So apparently, minimum uncertainty is connected to entanglement, and that is very neatly given in this paper by Haridas in 2013, that if you have, and this is of course proved for qubit states, that if you have entangled states, then those states can never achieve the lower bound of the uncertainty relation. Okay, this is proven. In fact, they proved that this is possible even for infinite dimensional Hilbert space for particular class of states, some special states. Okay, so in a way, minimum uncertainty is connected to entanglement, at least for the qubit state we see. The other paper, which is here the 10th reference by G. Toth et al. In PRL in 2007, is that they talk about spin squeezing inequalities. So they basically derive spin squeezing inequalities. And you know that squeezing is basically connected to uncertainty relations. So what happens is if the fluctuation in one of the observables falls below the allowed limit, then the state is squeezed, right? So in that particular observable. So they derive a set of spin squeezing inequalities, and then they study n qubit states again, and they see that if this is violated, then the state is entangled. It can detect entanglement with the violation of this kind of state, and assuming this is an n qubit state again. Another work that has been done again with the set of inequalities that were derived not particularly for, let's say, the spin angular momentum states and so on, but they were done for arbitrary observables. So there are a set of inequalities given by Guéné, and this was published in 2004. This should have been cited in the reverse order, but anyway. And in this set of inequalities, after they derive it, they basically are able to detect bound entangled states, again for qubits. And in fact, they just don't do it for bipartite state. They can also do it for multipartite entanglement. If those inequalities, I'm not writing down the inequalities here because those are set of many of the inequalities. And for every particular case, for example, if you're looking at the qubit state, the different set of inequalities apply, and bipartite different ones and multipartite different ones, and so on and so forth. But what I'm trying to say in all this is uncertainty is very much connected to the entanglement. And as I told in the beginning, I will not be talking about entanglement. I will be focusing on the uncertainty relation. But we have derived in the paper that I'm going to be talking about, we have also derived the entanglement for higher dimensional systems, criterion for entanglement for higher dimensional systems, basically. Okay, so now we come to the actual problem. Now that I have done all this, that uncertainty is, of course, important, and the sum uncertainty relations are important for particular reasons, and then they are connected to entanglement as well. So now I have basically two motivations. Number one, I wanted to look at SUN type of uncertainty relations and the sum uncertainty relations, which are state independent in their bound. So I want to get rid of the state, right? So that is one thing. And the other one is, of course, I wanted to establish some entanglement criterion for the higher level system. So these are the two motivations. Now, let's get to the basic ideas before we can get to the uncertainty relations that we are derived. And let me state what we have done. So we have basically derived uncertainty relations for compact classical Lie algebras. And these are some uncertainty relations that we have found out. And this is a big class, but we will be talking here only about the SUN, because SUN is the most familiar to us physicists. Okay, so for that, in order to give the SUN uncertainty relations to you, I need to talk about some basic ideas, the group theoretic ideas, which you have probably covered in your class if you have done your group theory course. So for us, in physics, we look at the matrix representations of Lie groups. That is what we are concerned with. Okay, and we call it SUN. So basically for us, the Lie group is an assembly or a group of n cross n unitary matrices which have the determinant 1. Okay, this is how we talk about SUN. But we can associate an algebra to these groups, And that will be denoted by this curly SU. So whenever I write SU straight, I mean the group. And whenever I write the curly SU, I mean the algebra. Okay. The Lie algebra SUN corresponding to this SUN group can be identified with a set of traceless anti-Hermitian D cross D complex matrices with a regular commutator, which is the Lie bracket in case of Lie algebra. So this sounds like complicated definitions, but I'll come to the simpler case and then it will be rather clearer. Now, the Lie group and Lie algebras have a correspondence, and that is exponential correspondence. So apparently, if you have the infinitesimal generators in the algebra like Lx, Ly, and Lz, you can construct the whole representation of a group. Okay, things will be clearer as I promised. But for the time being, we can say that the special unitary group SUN is a Lie group for the concern here, right at this point. And the Lie algebra SUN will be denoted by SUN corresponding to this SUN group, and will have n square minus 1 generators, right? I'll tell you how. But before that, I will talk about something called irreducible representations. Can somebody tell me how can I get rid of this here? Okay, apparently I can't, so I have to put up with this. Okay, anyway, so for irreducible representations, let's say that gamma, gamma prime, gamma double prime are representations of a group of dimension n, A and B respectively. Okay, so gamma is one representation, let's say, of the dimension n, gamma prime is of the dimension B, and this is, A and the gamma double prime of B. And as long as I can find the unitary matrix of dimension n cross n, so that I can write the representation, which is n cross n, in this block diagonal form, such that these two are the lower dimensional representations of the same group, then then I can say that this is a reducible representation. Okay, but if this is not satisfied, then it is an irreducible representation. And I'm sure that you have learned this in your textbook, but now we will be using a shorthand for this, and that is called irrep. I will be saying irrep a lot, and that means irreducible representation. Okay, so we have revised what an irreducible representation is. Now, my problem is, given a Lie algebra, I want to find the uncertainty relation. That is precisely the problem now. So what do I do? Let's get to the simplest case of SUN, which we are familiar with, our most favorite SU2 angular momentum operators, for example, which we have done in the basic quantum mechanics course. What we see is the SU2 algebra we can span by the set of generators called J plus minus and JZ. J plus minus are defined like this. And JZ and J plus minus have the commutation relations of this sort. And J plus and J minus mutually have the commutation like this. Okay. Now, I'll repeat again. So if you have the algebra SU2 of the angular momentum operators, you can span it with three generators. This JZ is our diagonal operator. Okay. And these J plus minus are called ladder operators. This is also called Cartan operator. This is another name of the same thing, Cartan operator, and these are the ladder operators. Those are not Hermitian operators, basically, defined like this. And these three can together span the whole algebra of SU2. You can know everything about it. Now, if you want to construct a representation of this SU2, you can construct a 2J plus 1 dimensional representation of this SU2. You have done all this already. And you know that when you do construct this 2J plus 1 dimensional representation, you will be getting these sets of set of states called JM, where your M there will be two indices, basically J and M in the states. And this M can vary from minus J to plus J. This is all very well familiar. And this basically is the basis state for this particular representation that you have constructed. Okay, and how it works. So if you take your diagonal operator and try to operate on your state Jm, you are going to be getting this eigenvalue m. You have your ladder operators, you operate on the state Jm. This will give you a number. This whole thing is a number, and then it will either take the state up or down. So the ladder operators basically take the states up and down. Okay, and this is the diagonal operator that gives you this eigenvalue in here, which is used for a very special purpose. This is the eigenvalue that m associated of Jz associated to the eigenvector Jm or the state Jm, and this is called weight of the particular state. So no matter which state you choose here, as long as you operate Jz on it, you will get the weight of that state. Okay, so what is going on here? We have an SU2 algebra, which can be spanned by these three operators, a diagonal one and two ladder operators. Then you can construct a representation of the corresponding group of SU2. And if you are in a particular representation, you will have to, of course, label it with something. But even before that, when you construct the 2j plus 1 dimensional representation, you get these states. They work in this fashion. The operators either jump from one state to the other. Okay, and our Jz does its job. Now, this eigenvalue, this particular eigenvalue that is associated with the eigenvector Jm of the diagonal operator is called the weight of the state. I know I'm being repetitive, but this is very simple. Now, you use this weight for a particular state. That weight you use to label the representation, because there can be several such representations and you want to see which one are you in. Okay, so this is how it works for SU2. Now for SU11, again, similar things, but in this case you cannot, you do construct an infinite dimensional representation of SU11. The operators basically do work in this fashion. Again, they're ladder operators, there is diagonal operator, and they take the k plus and k minus, take the, okay, this should be k minus, I guess. They take the states up and down. They do the same thing. Now, you see that there is lowest weight state that I have talked about. So there is a lowest weight state and there is a highest weight state in here that will be used for a particular purpose of labeling the representation that you constructed. Okay, and we will get to that, but this is how the SU2 and SU11 work. Now let us try to generalize it to SUN. How will it be spanned? It will be spanned by these Cij operators, where your I and j can vary from 1 to n, and I and j will not be equal. And these operators are basically your j plus minus like operators, the ladder like operators, and the diagonal operators, which are given by H again, the Cartan operators, they are also known as Cartan operators, and they will be defined in this fashion. So if you just want to reduce it to n is equal to 2, you can see that you will get your j plus minus here and you will get your jz here. Okay. Similarly, for SU3, you're getting in the higher dimension. And they follow a particular algebra, which is given by this commutation. And this commutation relation basically is an identification of the algebra. Okay, now once you have the spanning of the algebra, you can always have a unique state with all the non-negative integral weights. And when I say that, what is the weight? You have to take your diagonal operator and operate that on the state, and you'll get the weight of the state. So you can have a unique state which will have all the non-negative and integral weights. And if you try to operate or you try to put all the raising operators on it, you will see that it is getting annihilated by all the raising operators. And that is your highest weight state. Similarly, there will be a lowest weight state if you use all your j minus like operators and you see that it is getting annihilated. Okay, so this particular weight, that will be that will be your about your highest weight state is used to label that irreducible representation, that particular irrep. It will be clearer again. So let's get into the SU2, for example. So here we are talking about what j is equal to half. This is 2. So in this, you can get all these states in here. And you know, these are simply JM states, right? And this state, which you can also say j is equal to 2, or you can say m is equal to 2, this particular state that is 2, 2, is going to be used to label this irreducible representation, which has all these states, because this is your highest weight state. Okay. Now, similarly, in SU3, your operators will look something like this. So these are all your Cij operators. You are now, for n is equal to 3, right? So obviously, you will have your Cijs accordingly and your Cartan operators accordingly. And you can have a representation like this. So this is particular irrep of SU3, in which you will figure out all these states. So these are states, and what I'm writing in the brackets are basically the weights of those states. And this is the highest weight. So if you take the state corresponding to this, and you try to operate your ladder operators, all the raising operators, you will see that this is annihilated by all the raising operators, which is why this is being used to label this particular irrep. And we call it 0 to irrep. Okay, so this is how it works for SU3. Now you will notice one thing here, that if you construct the states corresponding to all these points, you are going to be having 3 indices in those. So when you are writing the weights, you will have these 2, and when you write the corresponding states, you will have 3. Okay. Similarly, if you have the m is equal to 2 irrep, you will have the weight only 1, 2, and then that is you're using to use the to label the irrep, but the states have 2 indices, JM states, right? So this is how it happens. When you go in SUN, for example, you will have n minus 1 indices to basically label an irrep, or if you want the weight of the states, but you will have n indices to have the states in a particular irrep. Anyway, this is all, I'm hoping, a revision. Similarly, in a more complicated irrep of 5, 2, it looks something like this. But again, you choose your right state that gets annihilated by all the j plus minus j plus like operators, and that will be used to label this particular representation in which there are these states. Okay, now what we do, why did we try to understand all this? Just because I didn't want to throw a lot of technical jargon on you, and you know what those terms basically means. This work itself, or the idea itself, is pretty simple. So we know that when we are dealing with SU2, we have this jx square plus jy square plus jz square is equal to j square, and that is invariant. Right? So what happens when I say it is invariant, you take this and act it on any state in an irrep j, and it will give you this fixed value jj plus 1, where j is labeling the irrep, right? So this is what it does, and this is called quadratic Casimir operator. Okay. Now let's get into a particular basis, where you know, in the particular basis of jz, where your in the particular basis where your jz is diagonal, basically what I mean to say, and in that the expectation values of jx and jy will be, of course, 0, and the jz will be m. So if we have this, if we are in that particular diagonal basis, in that case, we can simply write from here, we can expand this quantity on the left-hand side in this way. Why? Because some of this jx and jy expectation value are going to be 0, and you have the jz's expectation value. So if you work it out, apparently you combine this with this, you combine jy with this, jz with this, you will end up having this fluctuations, which we are concerned with in the uncertainty relations always, plus a term that will come from the eigenvalue of jz, which is m squared. Right? So this is just tricky way of writing it in such a way that you end up having, now from here, you can have this inequality, basically. First, you can have this equality, where you have your delta jx square plus delta jy square plus delta jz square. And we are doing this in a particular basis in which jz is, diagonal. So gets out to be jj plus 1 minus m squared. And then from there, of course, you can write down because what can be, what can your j take the values? Your m can take the values from j to minus j, right? So this is what is going to be giving the maximum limit. And then your uncertainty relations of SU2 algebra will be it will be bounded by j, which is basically labeling your irrep in the SU2. Now, in this case, it is j. You can also, so SU2 is so simple that you can also use m for it, because apparently they will take the same value, right? For if you are going to label the irrep, but that is not what happens in the higher dimensions, for example, in SU3. Now, if you have this uncertainty relation or this inequality, which will work like uncertainty relation if you wanted to put a bound on the fluctuations, on the sum of fluctuations of these, operators. Now, this saturates for your highest weight states and lowest weight states, as we already defined, and those will be jj and j minus j. You can check this easily. So in that sense, these are tight uncertainty relations. And this is not a new result. This is very well known. So if you want to generalize it, what do you want to basically do? You want to identify your eigenvalue of the Casimir operator that you had, quadratic Casimir operator, so to say, that was your jj plus 1. And then you want to be in, of course, you want to be in such a basis that is your diagonal basis. So let's try to think about it. So when you take any compact classical Lie algebra, for example, it is by design such that all the Hermitian operators will come in pairs, the jx, jy like operators, and they will close on to sub-algebras that are SU2. So for example, in SUN algebra, there will be several SU2 sub-algebras. So you can apply the same idea, and we can basically generalize this result. So if you are in the weight basis, which means again Cartan basis, and as it says, eigenstates of the Cartan operators, each operator of these Hermitian pairs will take the zero average value, which means that if you think about SU2, your jx, jy has the expectation value z. It's the same thing. So what we need to do is we need to replace the jj plus 1, which was the eigenvalue of the quadratic Casimir operator, by an appropriate eigenvalue of the quadratic Casimir operator in the higher dimension, and then m squared by the sum of squares of eigenvalues of Cartan operators, right? Because once you are in that particular basis, all that is going to contribute is the jz-like operators, and so your m square, which was the eigenvalue, m was the eigenvalue of the jz operator. So as long as you have all the similar operators, their eigenvalues will count there, okay? Okay, now killing form is something, again, a technical thing that is going to facilitate you do this, okay? So what happens is you can write the quadratic Casimir operators in the form of in the killing form in this way, where this n is some overall normalization that you are using. So what happens? We have a Lie algebra, let's assume for the time being SUN type. We span it with the help of our diagonal operators, jz-like operators, which are these. And then the rest, L minus R non-diagonal operators, which are jx, jy like operators, and in turn j plus j minus like operators, which are ladder operators. And you can write down your C2 in this form. Apparently, when you are in the convenient basis, in the diagonal basis where your killing form is diagonal. So what you do is you are trying to look for a basis where your jx, jy like operators become 0. Okay, so apparently when you are in SUN, as long as you can have your killing form diagonalized, that purpose is served, right? So again, you are trying to write these sum of fluctuations for all the generators of the algebra which act like operator in this way, which is what you also did. Eigenvalue of the quadratic Casimir operators minus this particular expectation value squared summed over all the diagonal operators. So that is what we basically do, and we can write it like this. It gets simplified, but after a lot of technical stuff that I'm not going to be basically talking about here, but it can be simplified in such a way that it can give you apparently a quantity on the right hand side that is going to be depending on the irreducible representation or label of the irreducible representation that you have chosen. Okay, so this lambda that you see here is basically the dominant integral weight, which can be defined like this. So you take all the weights corresponding to each index in the representation and then sum it over. And that way you get the dominant integral weight. And then you get, so if you have learned about calculating the roots in group theory, which I did not talk about here, so you can calculate the roots, and this delta is the while root, which is which has to do with the sum of all the positive roots in the in the particular array. So once you have those two things, then you can have your uncertainty bound, which is given by this. And this is the general, let's say, for SUN. It works for other type of algebras as well, but we are focusing on SUN, as I repeated several times. We can try to calculate this for SU2, SU3, SU4, SU5, and we can get the bound. The most noticeable part is this right-hand side depends only on the representation that we are choosing to be in, okay? Only on the irrep that we are choosing to be in. So for example, if you use the same rule and you calculate this, which I'm not doing here again, you calculate this right-hand side, you will end up, but you can trust me on this because this is a published paper. So you will end up having on the right-hand side your J, which was what? Which was basically the label of your irreducible representation that you chose for your SU2. So this is the uncertainty relation that I started with, but by using this SUN generalization, you can get to the same thing. For it also works for SU11, for example, and the sum of these fluctuations in all the generators is going to be bounded by K. Okay, and K labels the irrep that we are in. Okay, so this covers all the SU2, this covers all the SU11. Similarly for SUN, as I already wrote it down, but if you want to get it for SU3, for example, you will have more indices because as I told you, as you move in the dimensions, you're going to be having n-1 indices here. Okay, so for SU3, let's say that the irrep that we are choosing to be in is lambda1, lambda2 randomly, right? It can be the 5-2 that we gave the example of earlier. And we can easily derive that this is going to be the bound 4 times lambda1 plus lambda2. So it is just depending on both the indices of the irreducible representation that we are working in. Get to SU4, and there will be 3 indices that dictate which representation you are in. And now you can have the right-hand side of the some uncertainty relation depending on lambda1, lambda2, and lambda3. For SU5, you will have 4 of those, and then you will get this in here. So it works for SU3, SU4, SU5, and we did not stop at this. We actually checked those numerically. So even though it is very well established theoretically, we did check and it all works. We also saw that it should saturate as usual. For the JJ, for example, in SU2, your uncertainty relation should saturate for the highest and lowest weight states, right? And it does. So all these also saturate for the highest and lowest, corresponding highest and lowest weights in the irrep. So it all works very neatly. So this is what it says. It saturates for highest and lowest weight states, basically. And you see that we could, in a sense, get rid of the state for the lower bound. But still, we are depending on the irreducible representation. But it was mathematically a very nice, structure to see for the SUN. And I am honestly not aware of any applications, but maybe one of you can point me to an application of SU3 or SU4 uncertainty relations that are in some form and that can be useful. Okay, so that was the idea. Now to conclude, we created or we established a general procedure to construct some uncertainty relations for any classical compact Lie algebra. It works for any classical compact Lie algebra, which is a subclass of Lie algebra. And we have numerically verified, which was not terribly needed, but we did numerically verify it for n up to 5, and it can be extended to SO2n, SO2n plus 1, SPn algebras, and so on and so forth. And then, following the pattern of many other papers that try to connect uncertainty with entanglement, since our result was more general, we also talked about an entanglement criteria that evolves from this inequality that we established for compact classical algebras or this particular class. We figured out that this is an inequality that has to be followed for entangled states if you are looking at an n-partite state. An entangled state, and they have SUN, they follow SUN algebra in general. So in that case, in your left-hand side, you are going to be taking these fluctuations in all the generators of the algebra and sum it, sum it over how many generators you have. So those will be n minus 1, of course, for example, in SUN. And then on the right-hand side, you are going to be calculating this value, and this sum is over m, and this sum is basically over the rest of the observables that you have, the rest of the operators that you have other than these operators. So this is a bit tricky, but if you think about it, it can be really boiled down to the same SU2 criteria for, let's say, for example, spin half particles. If you take the entanglement criteria that has already been established in one of the papers that I cited above by Toth et al. So in that paper, this thing can be reduced to that criteria or a couple of other results that were given for special cases. So it all works very neatly for the uncertainty relations and also for the entanglement. So I think I would stop at that. And if there are questions, I would certainly like to take those.
I think there are not much time, but 5 minutes we can do it for the question answer session. We have already taken almost 1 hour.
Are there anything in the chat box? Maybe we can take 2 minutes, couple of questions.
Yeah. Few questions here. So, students, please ask the question.
See, it's very amazing that big piece of work. I can imagine why you took so long. Because this is a very elaborate work. Huh? I have seen it, but I have not gone through it. But maybe I have a question. Can I ask a question?
Please, sir, go ahead.
Please, yeah.
See, tell me, systems like, for example, proton, neutron, just like we have singlet, triplet, where, Bell state kind of thing manifest, maximal entanglement finds some physical meaning. Similarly, like proton, neutron, or anywhere S2 appears, you see the physical meaning of the kind of inequality which you have got.
Okay, so if I understand the question correctly, of course, it does work, for example, for spin half particles, right?
I'm not saying, Namrata, I'm not asking in terms of work. I'm saying, for example, the singlet state, triplet state physically, manifest. Maximal entangled state physically manifest. In magnetism, they do manifest, and energy, because of entanglement, significant contribution of energy is there. Entanglement in that sense is physical. That's what I'm saying.
Right, that's correct. So to be honest, I haven't really thought about it, but I would think that this can be used for such physically possible maximal entangled states, for example.
Okay, thank you.
So there is one question in the chat box. Maybe you can answer.
Do I have to see the question, or you will please read it for me?
It's in the chat box. You can read it.
Okay, because I was sharing the screen. So
you can just. Should I read it for you?
Yeah. It's okay. I can read it now that I'm in here. And in the chat box. What is the effect of time reversal on the Hamiltonian and its perturbation on Berry phase? Okay, so I'm not an expert on Berry phase, to be honest. So this is the question that I would not be able to answer, because this is related to Berry phase, and basically the person is asking that what is the effect of time reversal on the Hamiltonian and its perturbations on Berry phase. Yeah, I'm sorry about this.
Maybe you can discuss it later. So I think we should close it now. So let us thank Namrata for a very nice talk.
Thank you so much.
Thank you. So now the next talk, Mosme is around. Mosme is here?
Yes.
Yeah.
Am I audible?
Yeah. So the next talk is by Dr. Mosme Das from IISER Kolkata, and she did her BS and MS from Calcutta, and then moved to do ISC Bangalore, did her PhD with Professor Ram Sesa, and then went to the, I think, United States, did some postdoc, and came back and joined IISER Kolkata as an assistant professor. Now she associate professor, and her field of expertise is basically the quantum many-body theory, and she mostly works in the condensed matter theory. So with this small background, I request Dr. Das to present her talk. Dr. Das.
Thank you. Yeah, thank you, Professor Tiwari, for a nice introduction. And I'd like to thank everyone, like all the organizers of QIT, just inviting me for a little bit of lecture on my research, and also especially on DMRG. So let me share my screen. So if I share my screen, there is a one participant can share at a time, or a multiple participant can share it simultaneously. Can you see my screen now?
No. Click on the share screen, and then you go on there, your PPT will be there. So just click there. So first you click on the share screen, and then one box will come. There your name of the file will come. You have to click there.
Yeah. Share a screen. There is options called one participant can share at a time, or multiple participants can share simultaneously. I think I have chosen only one of them. If I do that, is there any PowerPoint somewhere? View.
No, we cannot see your PowerPoint.
No, it should show automatically, right? Like
No,
if
no,
I
so
just...
but once you click on the share screen, one
Oh
dot
yeah, yes,
will
I
come.
understand. Okay, now.
Now
It
it's,
was
yeah,
not
now
coming. Yeah,
now it's
it's
coming.
not coming at all.
Now it's
Okay.
fine. It's looking
Okay.
perfect. Yeah.
It's fine now? Okay.
Yeah, it's fine.
Thank you very much. Yeah, first I would like to actually thank the organizers, Professor Panigrahi, for giving me an opportunity to talk today. And the title of my talk is Application of Density Matrix Denomination and Group Technique in Studying the Low-Lying Excited States in Quantum Systems. So, mostly as Professor Tiwari told me that the area of research is based on theoretical and computational sciences in many body quantum systems. So, as all of you know that you have been actually attending lectures for at least a month or so, solving a Schrodinger equation for many body systems is not a trivial job for both in physics as well as in chemistry community, irrespective of the types of Hamiltonian we choose. Either you choose spin Hamiltonian or any correlated model Hamiltonian for fermionic or bosonic systems. It's already a difficult job for us to solve it exactly. So in physics and chemistry, most of us actually consider the stationary state wave functions, and we solve the problem of H psi is equal to E psi problem, where H is the total Hamiltonian operator and the E is the total energy operator. The wave function, the psi, it can be written as a linear combination of any basis function. So now this basis function is in our hand. Like depending on the Hamiltonian that you are going to use it in your calculation, the basis function is up to us. You can choose an orthonormal basis function. If you are using molecules, you can choose a basis set of atomic orbitals. It can be a orthonormal as well as a non-orthonormal basis. So basically, it is up to us. So numerically, if you want to solve such a equations, one has to write down the total Hamiltonian operator in terms of a small matrices. So matrices in the basis of the chosen that you have used it. So now this already told that depending on the Hamiltonian that you have used, either it is spin, either it's a correlated fermionic or bosonic system, otherwise it is an ab initio molecular system, the choices basis will differ from each other. Suppose we consider about just a spin-off system. Suppose we have a small atomic site, and each of the atomic site is represented by only one spin. You know, this if it is spin-up system, I can think about the spin-up can be a up spin or a down spin. So any one of the two possibilities for a spin system can occur. So the degree of freedom per site is actually 2 for spin-up systems. So if I try to think about n number of such spin systems, are actually try to calculate the energies or the ground state energy and the excitation gaps for n number of such one-dimensional systems, the dimension of the Fock space will increase to 2 to the power n. So you can see, depending on as we increase the size of the system, even for the spin, the dimension of the Fock space increases dramatically. If we consider for the case of a fermionic system, fermionic means I am thinking about the electrons. Because you know, according to the Pauli exclusion principle, the electron can, in a particular site, 2 electrons can reside, but their spin should be opposite. So one can think of for a fermionic electronic system, which actually resides in one of the particular atomic site, it can be it can give us a 4 possible ways of thinking. Like it can be an empty state where the electrons are not there, but it can think about an electron which is in a down spin. Like here I do it like a down spin the state. Here I have used like a representation with a binary digit. Suppose if I think about an atomic site, I would like to see if there is no electron is there. So I say the state is given by only 0, 0. This is a 3 binary digits. That corresponding decimal number is actually 0. On the other hand, when it is a down spin, I represent is like a 0, 1, which is actually a corresponding this decimal number is 1. If it is an up spin, if represented by 1, 0, which is actually a binary number 2, and if they are doubly occupied, I would represent it simply by 1, 1. This is a binary digit, and a corresponding decimal is equal to 3. So you can see from 0 to 0, 1, 2, 3, these decimal numbers are, that is a small basis for each atomic site in case of a just simply fermionics model. So if I think about two such atomic sites, they are adjacent to each other, and if we want to calculate what will be the total basis, if we want to use it as a for our calculation, I can say 4 to the power 2. That means 16 of such states I can generate. And in using the any normal coding, it's very simpler for us to calculate from 0 to 15. These are all like decimal numbers, and I can have written down what stands for what are the binary numbers which stands for each and every atomic site. So that means when you go for one atomic site to two atomic site for harmonic system, you are encountering 16 subbases. So now you know the Hamiltonian line going to be a little bit bigger, right? Earlier it was just 4 by 4, now it has been 16 by 16, only just adding one particular atomic site. So one can still reduce this basis by just thinking about the symmetry operator. If your that particular system is when the Hamiltonian of the particular system commutes with a spin operator, we say the spin and the Hamiltonian itself has a common set of eigenfunctions. So one can actually still reduce the basis if we want to target the singlet state. That means mostly when we talk about the energy calculation of a ground state, we call it as simply the singlet state. So if we want to calculate the singlet state, we can see for n equal to 2 atomic sites, the maximum number of electrons, suppose I have number is equal to 2, and this combination should give rise to only ms is equal to 0 state. That means I am just targeting the singlet state. So what are the possible states that I could look into that? So out of this 16 states, only there are 4 states, you see, they are satisfied the condition that I have actually put in. That means this particular site, one of the site is a W occupied because the number of electrons is 2 and their ms is equal to 0. Similarly, if this is correspond to the decimal 3. For corresponding to decimal 6, you see, one of the side is actually downspin, another side is an upspin. The total number of electrons is n equal to 2 as well as the total ms is equal to 0. Similarly, for the 9 also and also 12 also, you see the same condition is going to satisfy. So out of the 16, I could reduce to 4. So that means now if I want to calculate the ground state energy for the 2 electronic system in 2 atomic site, for the 4 by 4 matrix, if I diagonalize, I'll get this energy. So this is how I can reduce the dimension of the space. But this is not actually the solution. I can take it because number of sites, if I increase for the 2 site, I fit 4. But if I increase to 4, it's going to 36. For 6 to 400, and if I go to 14 carbon atoms, for only single 14 carbon atoms, the number of bases is actually nearly more than 11 million. So that means, you see, although I have implemented the symmetry, although I have reduced the space, it is still a very difficult job for us to calculate the Hamiltonian or to take the diagonalized value of the Hamiltonian to get the property, to get the ground state and everything. So that is the reason it is a very difficult job, not even for the classical computer nowadays, where whatever that we are using is very difficult for us to go beyond certain limit of atomic sites. If we do want to do exact diagonalization, means that I will get all the energies perfectly. So we have seen that if n increases, the dimension of the Fock space increases. With that, the exact diagonalization of the Hamiltonian matrix is computationally much more infinite beyond a certain number of atomic sites. So we need to think about some robust numerical algorithm that will help us to actually combat the growing size of dimension of the Hamiltonian matrix. You need to have such a method or robust algorithm that is going to help us. So in that way, that although if we increase the size of the matrix, we are not losing the properties in that way. So that's approximate methods which should be numerically much more accurate than any other method that is there. So There is a paper in 1992 first came by S.R. White. He has talked about a new method he has invented, which is known as the density matrix formulation of quantum renormalization groups. So the renormalization group has been first invented in 1975 by Wilson, when he has to give a solution to the quantum problems in mostly he has used a numerical renormalization group technique that he has first introduced. But there is some flaw on those energy techniques that he has pointed out S.R. White in 1992. He has reformulated the old approach in terms of density matrices. And he has done a remarkable job in doing that, because this new approach is optimal in certain sense, he wrote. And he said the density matrix framework provides an important conceptual basis for numerical RGs. For example, he could show if I implement this energy, that a numerical RG with using the density matrices, he could solve the ground state energies for spin-up chain. This is an infinite spin-up chain as well as is equal to one chain. So mostly we see that this is found to be very much really very robust, not only for the robust in the sense numerically much more accurate, and one can use this particular method to various field of researches. So this particular paper is a landmark paper in 1992, where they have claimed also in going to be in near future, the DMRG will be the most popular technique when in computational field. And this is really which I feel after the 30 years, so nearly 30 years or so, DMRG is going to be, it is proven to be a very good method in the field of not only in case of physics, but also in chemistry as well as other research field. So let us first try to understand how this algorithm works. Like when he has given his paper in 1992, he has given an example of spin-half chain. Spin-half chain is an infinite chain where he has talked about a system which is we start from a small system size, and the small system size you have to take it in such a way it can be exactly diagonalization. Means like one can actually get the eigenvalues and eigenfunction exactly. Because it's a small system, one can think about writing down the Hamiltonian in a chosen basis, and we can get the ground state and as well as an excited state energies and everything. So once we the total system is named as a super block. So one can actually divide the super block into two separate subsystems. One is system as well as another is environment. Here, for the simplicity, I showed it just a mirrored image. The system and environment, they are the mirrored images. But one cannot say that it can be always an identical size. It can be different. Whether the system can be a different size, environment can be a different size. Okay, so that is for the simplicity. We try with some system which is actually identical to each other to start with. So I would say the system blocks the left side and the environment is on the right side. They are identical to each other right now. So one can write down the ground state eigenfunction G4 as just a direct product of this system and the environment. That is the left block as well as the right block. With these are the coefficients. The they are the coefficients of the ground state wave function that we have solved exactly. So with this super block, now since we have cut this super block into two separate subsystems, one can calculate the density matrices of the left block. How we can calculate if Ci corresponds to, these are actually the coefficients of the ground state wave function for the bigger block. So one can calculate the smaller block density matrix, that is the reduced density matrices, taking trace of all the environmental states that we have. So it's basically when you calculate the density matrix, you know we have to just multiply the coefficients. So if you don't lose the dummy, you have to put a dummy indices so that we don't lose the generality. So Ci star Cj, you think about this is the Ci star Cj, where all the C here is actually real. So that is the reason I didn't put any star here. Star is no complex conjugate here. So while doing that, I have to trace over all the right block, that is the R2. R2 stands for the right block for the system 2 here. So once you do that, you will get now the density matrix of the system here. If the system density matrix is, of course, the dimension of the density matrix is very small. Suppose the dimension of the total Hamiltonian was actually n cross n. Suppose that we start with an n cross n, that is for the small system. So once we got the reduced density matrix, now our job is to diagonalize this density matrix. So what is diagonalization is all about? Once we diagonalize density matrix, we'll get all the eigenvalues and that's corresponding eigenvectors. So eigenvalues are very important. So if we see some of the eigenvalues are very small, we will discard their corresponding eigenvectors in constructing a transformation matrix called O2. So O2 will keep those eigenvectors, whose columns are will be those eigenvectors which corresponding eigenvalues will be actually highest, or you can say largest. We will not keep all those eigenvectors which corresponds to some eigenvalues which are very small. So mainly I can just tell you, suppose you have after diagonalization, you will get some 10 eigenvalues, and you will see out of the 10 eigenvalues, 7 of them are actually some non-zero values are coming, but other rest 3 eigenvalues are very small. So we use just discard those 3 eigenvectors while constructing the O2. So O2 will be now having a dimension of n cross small m. If we put m is actually the number of eigenvectors with largest eigenvalues that we keep. So here the concept of truncation is coming to picture. Suppose we are going starting for a very small system, for 2 systems. In that case, m can be equal to capital N, because that can I do not need any truncation. But as we increase the system size, you may appreciate this value of that n will going to increase more and more. In that case, we have to truncate the basis. So once we do this, so you get during the construction of this transformation matrix, we will keep only the m number of eigenvectors with largest eigenvalues. That is much more important. The value of m is always less than or equal to capital N. So when you have the transformation matrix in our hand, what we'll do, we will try to renormalize the smaller subsystem, all those Hamiltonian, in terms of this density matrix eigenvector basis. We could how to renormalize it? We can use this only a matrix algebra like O2 dagger. H2 is actually whatever the original Hamiltonian matrices we have. O2 dagger, H2 and O2. In H2 tilde, these are the renormalized Hamiltonian of the left block right now. And you can see when we keep all those the eigenvectors, when m is equal to n, when we keep all those eigenvectors, this is nothing but a similarity transformation. Means we are changing a particular matrix from one basis to another basis, but the eigenvalues remain the same. So this is known as a similarity transformation. But if we truncate that one, still the properties of those Hamiltonian matrices are not going to change too much, because we are discarding only the eigenvalues which are not appreciable enough, which are very small. So in that case, we have seen using the similarity transformation, when you the tilde, that is the renormalized basis is now is the order of m cross m. M cross m means that is the cutoff value of m, which is must be less than capital N. Here, now the next step would be, now we have to augment the system size. So earlier we have not augmented, we are starting for 4 side. The next time onwards, I would like to augment into different spin systems, like spin hub systems. The red balls are actually, they are the new atomic site which I have joined in between this left and right. So we can see now how to write the total Hamiltonian right now. Total Hamiltonian comprises of the left block Hamiltonian, which is in the renormalized basis of a DMAB basis. Similarly, on the right-hand side, this is actually the mirror image of that. It is similarly in the DMAB basis. Now, we have to think about how to connect this renormalized basis to the, that is the new side that we have added, the sigma, is equal to half. So this S2, which is earlier in the spin operator, which is earlier in the Fock space, we can renormalize into a DMAB basis. That is, here we can say this tilde corresponds to DMAB basis. So S2 dot S3 is actually the interaction between this spin and that newly added spin here. Similarly, here this is newly added spin, that S3 and S3 prime, where the prime is actually the right block, they are actually in the old, whatever the old basis we have, that is not in the DMAB basis. So we can write down this in the operator form. Similarly, the interaction between the newly added side on the right block, sigma prime, it can so be actually dot product with the right block. So this is how actually the new augmented Hamiltonian will look like. That is for the 6 sides. So next time what we will do, again we have to renormalize the H6 in the DMAB basis to form the H6 tilde. But how we can do it? You know the mu is actually your DMAB basis and sigma is your actually the Fock space. So we can write down the total Hamiltonian will be right now in the form of mu sigma, sigma prime and mu prime. So in this case, the left block is actually mu and sigma because this only act on the DMAB basis. Mu stands for the DMAB basis here. In the other hand, the right hand side is actually in the right hand side is given by the mu prime and nu prime basis. Similarly, that wherever you have the tilde, whereas you have a tilde is already in the DMAB basis. But in this case, where you have only the S3 operator, which is newly added side, is in the basis of sigma and the tau, which is actually that we have added a new Fock basis. So finally, we can write down the total H6 Hamiltonian, that is the augmented Hamiltonian, in terms of the renormalized basis. This is H6 tilde. So next, we have to diagonalize this H6 Hamiltonian to calculate the ground state for the total augmented 6 sides. Okay, so 6 sides is given by, because we now this mu sigma is actually your total renormalized states. So one can write down this ground state for the 6 side Hamiltonian, just a linear combination of mu sigma and the direct product of mu sigma and the mu sigma prime, mu prime and sigma prime with the coefficients C, mu sigma, sigma prime and mu prime. So this is, again, we have to do the iteration process where this total super block again subdivided into 2 halves, which each of the half corresponds to only 3 sides. So you will get the Hamilton density matrices for the 3 sides. And then once we got this density matrices, again, this particular iteration is going to continue, and we'll again add another even 2 sides again to augment it to get the Hamiltonian matrix for the 8 sides. So this iterative procedure continues until and unless we will get the desired structures. Okay, so this is how we can see the total Hamiltonian of the left block and the right block. Each of the dimension of the matrix is actually m. So once you do the total Hamiltonian, augmented Hamiltonian, it goes to m square because we have write down everything in the direct product basis of mu sigma and mu sigma, mu prime and sigma prime. So in case of spin system, since I have already told for each an atomic side can take only 2 sides at a time. So total the matrices, the total Hamiltonian matrices should have a dimension of 2m square into 2m square. So once you get the biggest Hamiltonian, you diagonalize the Hamiltonian to get the ground state and related properties. So next, sorry. Okay, so next thing is that since I have already talked about the infinite DMRG approach, I'll talk about you that how the infinite DMRG approach, the first thing is give you an accurate results, but still one can actually improve the infinite DMRG results by improving it through finite DMRG approach. Why do you think about finite DMRG approach? Because when you talk about infinite DMRG means we are talking about a spin change of a system of spin half, which is actually a growing size. That means for a suppose 100 to 200 sites. For this is an open boundary condition. But if I want to think about a system which is a smaller size, suppose I want to calculate for the spin change for 10 site or 20 site, this is a finite system. So for the finite system cases, if you want to improve their energies, one has to can implement the finite DMRG approach, but it has to go first starting point would be your infinite DMRG approach. So first in the infinite DMRG approach, this is suppose you are to have already calculated for the total system. Suppose 12 sites problem you have calculated. This is you have already have solved through infinite DMRG. Then the next step, what we want to do it, you have to, this is totally symmetric system. You can see that left and right are actually equal to each other. So you can think about borrow as particular, you can increase the system block and then pushing the environment block little bit shorter, such that each and every time you take 2 new sites at a time within that block. But your system size is going to be the same. You're not actually increasing your system size. It's increasing the same. You're just putting different kind of system and you're taking different kind of environmental block. So you will do this iteration until and unless you will get to have just only a single ball here, single atomic site on the right hand side. That means you just during the sweep, the arrow is actually indicating the where from which direction to which direction you are going to sweep. So you are sweeping like this, such that you ultimately you would just go to the dead end. That means you have only one side here. So once you reach there, you will come back again. You just reading on the other side. You putting see the arrows here. You just follow this arrow until and unless you come to the again symmetric position. So come to the symmetric position again. That means wherever you started, you come back to here. You can still keep on doing this system when you just go into the right hand side until unless you on the left hand side you come to the dead end and then you go back to your like a middle point again. So this is the total iteration or practice is known as the sweeping procedure in DMRG. This will actually going to help you because for the beginning you have some constant energy, and each and every time you changing your system and environment size, you calculate that you just left subsystem, you calculate the reduced density matrices, renormalized it. Again, you do the same practice until unless you reach to a certain level where the symmetry exists, and you calculate again your ground state and wave function and as well as your energy. Your energy values will going to improve a lot. So this is one of the method, but still if you implement this the finite DMRG method, you first do to the infinite DMRG method. And this is DMRG, this is much more computer intensive. You can see for each and every step you have to need to take a record of all those operators because you have to renormalize them in every time. So the success story of DMRG does not end only for the open boundary system. So researchers have already started or they have already published some of the very good papers for implementing the DMRG, not only in the open boundary system, but also the cyclic boundary systems. Like I have shown you some paper by Dr. Manoranjan Kumar and their co-workers in 2016, because one can actually implement this DMRG with the periodic boundary condition. That means a cyclic system. One can also think about implementing DMRG in such systems like Y junctions. Like Y junctions has 3 atomic sites for each iteration. It's completely different from the 1992 DMRG that we have seen in SR white paper. So there is a lot of applications in DMRG. They are not only limited to only one-dimensional. One can actually think about quasi one-dimensional feature. They can use it this particular method in different the molecular architecture also. So there are other applicability of DMRG in different field of research. So although I have told you that originally it is applied for diagonalizing the spin Hamiltonian of interest in solid state physics, but it was also successfully applicable later on to fermionic system or bosonic systems with correlated electronic model Hamiltonian. It is also very efficiently applicable to study the cyclic or periodic boundary conditions quantum systems. In case of spin ladders also, it is a remarkable achievement by DMRG. DMRG gives a very good results and a Y-junction spin chain also, etc. Later on, DMRG is successfully implemented in case of the ab initio Hamiltonian treatment for molecules. Like in case of ab initio Hamiltonian, as you know that when you calculate the energies for a molecular system, ab initio Hamiltonian comprises of the kinetic energy of the electrons, kinetic energy of the nucleus, as well as the nuclear-electron repulsion and electron-electron interactions, and then electron-proton attraction. So all of this Hamiltonian we have to consider in case of ab initio method. So like other quantum chemistry methods, ab initio DMRG method is showing to be a very much powerful and the major advantage of this ab initio DMRG method is they are size consistent as well as they are very variational. Because like DFT is variational in the sense, but you may not get, it's always an upper bound energy that you get. So exact energy, you will get the energy in DMRG which will be in the upper bound to the exact energy. So now this, how do you know that how much accurate your calculation is? So how to calculate or how to quantify the accuracy part in DMRG? So we can see that that accuracy part, it depends on the value of m. M is actually this part of value that in DMRG that I have told you. So cutoff value of m actually decides how much the error that I can have in my calculations. So as you know that when you construct the density matrices, the density matrix eigenvalue, if we trace over the eigenvalues, I should get the value of 1. That is but ideal case. And if you divert from the ideality, then you have to see how much we have deviated from that. So if I have omega j is the largest eigenvalues of the density matrix that I have constructed, if omega j is given by this, but j is going from 1 to the m, is the cutoff DMRG cutoff number. So if I can calculate the epsilon value, which is a function of m, we call it as a truncation error in DMRG calculations. So the ground state energy per site, if we calculate for a spin-half chain in one-dimensional and also in the one-dimensional Hubbard chain, it was accurate up to 10 to the power minus 6, which is a remarkable number, even if we have only m is equal to 64. So that means if I just keep 64 cutoff value, the accuracy is actually very good in case of spin systems. Of course, spin-up system is accuracy 10 to the minus 6. So after 6 decimal place, the energy is actually going to match with the exact number. So while preparing for this talk on DMRG, I would come across some of the very good, interesting the papers which actually talks about the intimate relationship between the DMRG as well as the quantum information and quantum technology. So the quantum information theory also provides a measure of entanglement through the computing entropy known as the von Neumann entropy, which is the most fundamental measure in quantum information. So in this quantum information technology also deals with, suppose, a bipartite system like this, where we have a small subsystem called A and B. Even the similar we have seen in DMRG also deals with the bipartite system, which is the direct product of the two subsystems. So this is actually a similarity between quantum information as well as the DMRG technique. So each subsystem in general, these are the mixed state of the whole system AB. So one can write down the the full super block, or in quantum information technology, the HAB is actually a direct product of the two subsystem individual, HA a direct product of HB. So one could calculate the reduced density matrices that we have already know that from DMRG we know how to calculate the reduced density matrices by tracing over all the states on the other subsystems. If the rho is actually the density matrix of the full bipartite system that we have considered first. So one can calculate the von Neumann entropy, which is given by the essay. That is for the, this is the von Neumann entropy for one small subsystem A in the total system AB. So this is minus trace of rho A log rho A. So even this, using the DMRG also, one can numerically calculate this von Neumann entropy, because this we know basically rho A is, if the eigenvalues of rho is given by just only omega j that we know, and j goes from j is equal to 1 to m, we can simply write down the von Neumann entropy to be summing over j is equal to 1 to m omega j log of omega j, as the DMRG preserves the entanglement under renormalization. So even if you renormalize this Hamiltonian, the entanglement of the one particular subsystem with the total bipartite system is actually remain the same. So similarly, in the language of quantum data compression, like in quantum information, when scientists are very much thinking about how much data is going to lose in our entanglement issues. So this can also be actually calculated through DMRG, because in DMRG we have already talked about the truncation error that we have.
Ma'am, I have a question.
In that truncation error, so in that case, this particular value. Yes. Sorry.
Somebody wants to ask a question.
No, I'm so sorry. This is my actually not.
Oh, okay.
I'm so sorry. My child is actually taking online classes.
Oh.
So I'm sorry. Are you? I'm audible, right? I think you can listen to me, right?
Yeah.
Okay. Thank you. So DMRG and quantum data compressions is actually, they are, you can say, we can relate to this hand in hand in that sense, because epsilon m is actually our truncation error, and in DMRG that is also can be seen as an informational loss, measure of information loss in quantum information technology. So I have just given two like references. If students are actually interested, they can actually look into these very good, nice papers. And I am not an expert of quantum information and technology. And if you have some questions, then actually you can just go back and then see the references. I hope that you will have some question. You can just come back to me. I try to answer those questions. So now come to my own research. I would like to say that the application of DMRG technique that I have used in this either Kolkata is something little bit different, because I am interested in seeing because I work in the chemistry department, I'm interested to see that how the molecules are actually, energies can be calculated and their properties can be calculated. So in that is the case, I have used this technique to calculate the ground state and low-lying excited states of some molecules, which can be well described by model Hamiltonian approach, because you know the model Hamiltonian approach is actually the basic in using the DMRG. It will be faster for us to calculate through model Hamiltonian approach. So I have just shown you some of the molecules which are in chemistry language are known as conjugated systems, because these carbon atoms are actually they are connected through single and double bonds, adjacent single and double bonds, and each of the carbon atom, they are represented by a pz orbitals. So these pz orbitals, the electrons can hop from one pz orbital to another pz orbital, so that it can be interactive. So these are the list of the molecule. You can see most of the molecules are not linear at all. So unlike the cases of spin system that you have seen, one-dimensional one-dimensional chain of spin system where you have arrays of atom site. Here you can see that they are not in one dimension. They are basically quasi one-dimensional systems, like they have an x coordinate as well as y coordinate in different atoms. So that I can show you, this is the harmonic model, these are the harmonic system. I can show you for this kind of system also, geometry works very beautifully. So these are the molecules named like phenacene, this is the zithrine and pentacene kind of dimer. You can see these are just a fragment of graphene sheet. One can think of a fragment of graphene sheet, and they are actually molecules exist. So the objective of my research, why I'm interested in doing this, studying the energies of those conjugated molecules, because in comparison to inorganic counterparts, the organic conjugated system, they are cheap and eco-friendly. That is of course, but they are also used in the electronic devices like FATE, LEDs, and also the single molecular electronic devices, everything. But that is not the case already, because the most important thing is the electronic structure. Electronic structure, that is the energy ordering of low-lying excited singlet and a triplet states with respect to the ground state. Their energy ordering is actually gives you or dictate their properties most. That is I like to say. That is the reason I would like to say how the lowest singlet dipole allowed state S1 and the lowest triplet state T1, how they are close to each other, whether they are close to each other, and how if they are not close to each other, what is the like mostly you can see all those molecules, the triplets, lowest triplet state is actually lower than S1. So I want to know where the T1 lies and where the S1 lies, because depending on their positions, S1 and T1, they give lot of remarkable optoelectronic properties. So first of all, I would like to discuss the LED, that is the organic light emitting devices, and how it works. In organic light emitting devices, you can see that electron and hole recombines to give you light. So one electron and hole, both are actually spin-off systems. So one can have upspin or downspin. So when they combine with each other in non-interacting limit, one can think about just generating 25% of singlet state out of 100% and 75% rest are triplets. And in chemistry language, singlet states only give their emissive, they give the light. So when 75 triplets, mostly they are actually going to go to the west. They don't actually participate in the efficiency of the LED devices. So, but in case of correlated system, one can see this is not true. This is true only when we don't have any electron-electron interaction in the system. So in the conjugated molecule, this is actually a strongly correlated system where you have a strong electron-electron correlation. One can see there is a possibility that SO1 and T1 comes very close to each other. If it is very close to each other, so one can repopulate some of the energies from T1, so that T1 can goes to S1 in a thermally. Like if the value is nearly very small of the order of 0.025 electron volt or so, in that case, reverse intersystem crossing can take place, so that the T1 must be populated to S1, and so that the emissive power or the efficiency of the LED devices is going to increase. So this can only happen when the S1 T1 energy gap is very small for certain molecules. So similarly, there is another thing that we would like to consider for if this energy of S1 in such a manner that it is very of this S0 S1. Suppose there are the energy gap between this S0 S1 in such a manner, it is twice of the triplet energies. It is nearly twice of the triplet energy. So what happened in that case? Suppose there are two molecular chromophores are there. In case of solar cell applications, when you H2 is fallen onto one of the molecules, so one of the molecule goes to a singlet state, is an excited state, and one of the molecule remain in the S0 state. So S1 and S0, if the energies are something like this is the T1 is at the halfway between S0 and S1, these two energies will be redistributed among themselves to give you the two triplet excitons, two triplet chromophores in that case. This is how I have just tried to schematically I have to show you that how the from one S0 and S1 will give you two triplet states. So these are the thing that what is the need of what is the advantage of having two triplet excitons from one singlet exciton. It means that when you do the solar cell application, so the solar cell, when the energy is absorbed, most of the energy is going to get lost through non-radiative process. So if if we can think about some molecule whose energy levels, the triplets are actually just simply halfway between S0 and S1. So total energy will be used by these two triplet excitons. So more energy will not be going to be wasted like that. So this is the reason. So singlet fission, this is known as singlet fission technique, where singlet is going to give you two triplets. So this is going to be very much mechanism is implemented in case of solar cell application, so that we can use this such as molecules in solar cell, so that we can enhance the efficiency of the solar cell. This is how. So these are the two things that is actually interest me. So that is the reason I am using these molecules. So let me just try to tell you how the molecules emerges actually. The molecular Hamiltonian will look like in that sense. So I have already told you these carbon atoms are connected through just a pz orbital that I told, right? So each and every pz orbitals can have an electron or cannot have an electron. Maybe it can have a W occupied electron. So one can think about a Hamiltonian to start with, how the electron can hop from one pz orbital to another pz orbital with a transfer probability T. So minus Tij, epsilon, Ai dagger, Aj, this is already, this is second quantized notation. This is how the probability from one electron hops from one side to another. So Tij means the transfer probability. And epsilon I is the just orbital energy. Is summing over all the i's means that you are taking consideration of all the atomic orbitals present in the system. So this is totally a non-interacting limit. So there is no electron-electron interaction part here. So we call it in chemistry language, this is a Huckel model kind of correlated model, where you don't have any interaction between the electrons. And in physics literature is mostly known as a tight binding model. In solid state physics, scientists are mostly use tight bonding model, where there is no electron-electron interaction. But suppose if I slightly put an electron over there are two electrons inside of one particular pz orbital, then there will be on-site electron-electron repulsion term. One actually try to add up to this Huckel model. So this should be actually give you the physics notation is the Hubbard model. Similarly, when I talk about if I include the long-range electron-electron interactions, then with this particular model, then we can think about is known as a Parisot-Parpopol model, which is nothing but the correlated model for the conjugated system. So I have used this is the model Hamiltonian for all my calculations. So now I just give you a little bit idea how I have used or DMRG. I have used a DMRG in try to actually draw the picture of a molecule. Suppose I have my target molecule would like this. This is a dimer of pentacene with a small benzene ring. So I have started from a very small system according to the SR White's paper. The small system we have 4 atomic sites. So these are actually 1, 2, 3, 4. Start from 4 atomic sites. I keep on increasing, augmenting the size. At a time, 2 sites are added each iterations, until and unless this growing scheme we got it actually the total the target structure that we want to go for. So then the next question we can ask me, how do I know the structure that I have drawn and the energies I have calculated is actually authentic in the sense that if I have to compare every time with the exact dimension method technique, that is can be possible. Like with the suppose mostly whatever the computational facility I have in either Kolkata, I could go up to m is equal to 500 numbers. 500 is the cutoff value of 500 with all those mostly molecules. And for each iterative step, it is required to compare the ground state energies of the molecular systems obtained in DMRG to those obtained in ED, that is exact diagonalization. For a certain amount, for that value of carbon atoms, we can actually try to compare the energies, exact diagonalization energies of ground state as well as the DMRG number. It matches fantastically for this m is equal to 500. But of course, there is a process of improvement all the time. If we increase more number of values, which is very computationally demanding job, then we can actually goes to a very accurate values of the energies with the ED. So in this case, with correlated model, we cannot compare for a larger system. So what we do, we can use simply the tight binding model or non-interactive model and do the calculation and try to see how much the energy with the tight binding model in ED and how much we got it in DMRG. That should be comparable. So that is, if it's comparable, then we can check that our DMRG scheme works for this particular system. So I will just show you some of the work that we did for some molecules. The molecule's name is not more important. This is not a Z-string kind of molecule. This is one kind of graphene fragments molecule you can think. So we have similarly, this is the DMRG scheme I have shown you. This is of course not a one-dimensional chain. This is very difficult. The scheme is may not work. It is have too much of entanglement between left and right. So we have to grow this particular system each and every iteration very carefully until and unless we get the desired structures. And this particular molecule that we have shown that it is very useful or very interesting in singlet fission as a singlet fission materials and molecules. So there is another molecule that I have shown is known as the indenocycline ditherapine and indenofurin molecules, kind of molecules. This is also various values or energies of low-lying excited state energies. We have seen it. There is very much important in solar cell application as well as it can be also used in the LED applications. So this is starting from the small system. You can also see that how we have grown it from the left and right block. So only thing that I forgot to mention to all of you, is all this molecule that you have seen, they have some certain symmetries involved. So even though we have to, using the DMRG also, we have to use a symmetry. Otherwise, if the computation, it will be impossible for us to do the calculations. So we have used the C2 symmetry in that case. In both the cases, you can see C2 symmetry. That also reduces our dimensionality. So before I conclude, I should say that whatever the lesson today, I would like to convey to you that density matrix dimensional group technique is a very robust and very efficient in solving the correlated one-dimensional, quasi-one-dimensional quantum systems, including the spin, fermionic models in physics, and molecular systems in chemistry. If we have a proper model Hamiltonian, it is the accuracy of DMRG technique depends on the cutoff DMEB n. And the quantum information technology and DMRG, they have a very intimate relationship because one can understand the DMRG better in the language of quantum information, or the other way around is also true. So DMRG technique helps to calculate the measure of fundamentals in quantum entanglement known as the von Neumann entropy. Besides, in case of a bipartite system, it is very helpful for us using DMRG to calculate the von Neumann entropy. And also have seen in DMRG, wherever we have used the truncation errors, is related to the quantum information loss in quantum information technology. And DMRG techniques can be more efficiently applied to study the low-lying excited states of some conjugated molecules described by correlated model Hamiltonian in the field of optoelectronics that I have shown you. So with this, I would like to end my talk with acknowledging two of my students. So one of the students is graduating last year, Sumit Nosman. He is in the postdoctoral fellow in Institute of Inorganic and Applied Chemistry in University of Hamburg from 2021. Another senior most students there is Naomi. She is working with me, and she is mostly actually looking into the intermolecular singlet fission materials. I would like to acknowledge ISAR Kolkata for the funding and also the ACRB for the funding that whatever the calculation I did. And I also like to thank you all, Professor Tiwari, Professor Panigrai, and all the students. If you have any questions, please let me know.
Thank you, Mausmi, for a very nice talk. Now the talk is open for discussion. So students, please ask the question.
Shall I stop sharing this?
Yeah, you can stop sharing it.
Are there anything in the chat box, no?
Yeah.
Right now, I don't see anything.
Okay, I have a couple of questions.
Yes.
See, I mean, it's a really very powerful method, but it's primarily for 1D.
Yeah, primary pairs are 1D, but now I think scientists have a lot of things because the problem is that with the DMRG that it is 1D because if you see when I first draw the spin-off system, or if you case it into one dimensional, the left and right actually meets at a point. There is a point. If it is like if you try to minimize the area law, then it will be very much powerful. So that is the reason I've shown you for molecules that I have used it. These are not really simply one-dimensional. These are a quasi one-dimensional system. It is not actually increasing in the y direction, but there is a lot of y in it. And also I've shown you some y junctions spin chains. Correct. They are not simply 1D. So people are actually using more than 1D right now. But we have to make sure the entangle between the left and right should not be too much. The area loss should be minimized.
Okay. And this second question is that if I remember correctly, DMRT uses singular value decomposition, right?
Singular, I don't understand.
See, for example, given a density matrix rho, it can be, there is this theorem that it can be written as, even if it is non-square, it can be written in the form of some unitary matrix, some diagonal matrix and V dagger.
Yeah, that is true because so the density matrix that you have used you have to calculate to get the transformation matrix, right? So once you get a transformation matrix and then you renormalize, then you will see that this DMAB basis, that everything that you are putting in the DMAB basis. So that approximation of the wave function that we got, there is an approximation in the way that it is a value of M. So if you can have computational facility wise, if the value of M is very high, so the results will be much more robust, I can say.
Okay. Thank you.
Anybody else? Anybody else wants to ask question? If not, let us thank Mausmi for a very nice talk. Thank you, Mausmi.
Thank you.
So now I will hand over to the organizer.
Yeah. We are also taking a break. 7 o'clock. We have the last talk of today. Okay, thank you. Thank you, Asuni.
Yeah, thank you. So now we will close this session.
Yeah.
Okay. So now we close the session. Thank you all.
Thank you.